在我 face 是这个，对啊，非常在我 face
，Okay, have you checked out the lecture notes already? Yes, lecture. Anyone check already? Check. Not yet. Please read the lecture notes that I post, and let me know if you found any problems going on. Okay, so last time we talked about this group homomorphism. Yeah. So group homomorphism is a map from a group to a group. Okay, satisfy a property. Okay, or 宣言. What's the property that group homomorphism is satisfied? Identity No, that's not in the definition. What's in the definition? The commutative diagram. Huh? And then convenient B, domain B, by 5AB equals to IA. Okay, so that has to be true for all AB in the inner domain. Okay, and then the result is you have to send identity to identity. Okay, so talking about map, there are certain things that we are interested in. Okay, so first thing is we are interested in the image of G. Okay, so image of G is the place where G map the codomain to. And then the image not necessarily equal to the codomain. Okay, when they are equal, then the map is surjective. Okay, because every point has a pre-image. Okay, so what's the pre-image of a point? What's the pre-image of a point? What's the pre-image of a point? So a pre-image, okay, under a map is all the point inside your domain, okay, such that when you map X across, you get your image. Okay? So this is a pre-image of. So this is a pre-image of a point. So how do you think of it? So you have a point in codomain. Okay? You have element in your domain get mapped to the codomain. Okay? And then these elements form a set, which we call the pre-image or inverse image. Okay. Is it following? Yeah. And then if we have pre-image of a set, okay, then we need to consider all the elements that get sent to the set. So we have pre-image of a point of an element, then pre-image of a set. Is it okay? Okay. Okay. So for example, what's the pre-image of a image of G? Okay. Is all the point in G such that phi of X is in image of G. Okay. So be aware what is the sign, is the symbol I'm using here. Okay. This is equal, this is an element. Element and equal is different. It's take note. And then there's an interesting set inside G. Okay, there's an interesting set inside G. Okay. So this interesting set is what we call the kernel. What does kernel do? Okay, kernel are the things that get mapped into the identity. Okay, in codomain. Okay, so these are the things get mapped to identity. Okay. 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 And then what else? These kernel are actually subgroup. Okay, kernel is a subgroup. Image of homomorphism is also a subgroup. Okay. Image of a group under homomorphism is also a subgroup. Okay, so these are natural ways to get subgroup. Okay, and then if you look at the inverse image of a subgroup, okay, so let's say we have a subgroup in G prime, okay, we look at the inverse image, phi inverse, okay, look at the phi inverse. It also form a subgroup here, okay, phi inverse of K also form a subgroup. Okay, so there are three ways to get the subgroup using homomorphism. Any question? Now, this is what we proved last week, last lecture. Kernel of the homomorphism is a subgroup. Image of a homomorphism is a subgroup. And then pre-image of a subgroup is a subgroup. Any question? Okay, so let's look at some proposition. Okay. Is this as a proposition first? So homomorphism D is injective if and only if the kernel is just the singleton with the identity element. Okay. So one direction is easy. Direction you think is easy. Easier. Which direction is easier? Which direction is easier, do you think? Oh, from left to right? Left to right? Okay, let's try it from left to right. So suppose D is injective. And then we want to show that the kernel is actually just a singleton. Okay. So what's injectivity? What's injectivity? Yeah, what's one to one? What's one to one? Sorry? Different different element get sent to different element in the hologram. Okay. So how we rephrase this? So note that if bx equals to py, then then x equals to 1. Okay, so this is the contra positive you say. If x and y is different and fx doesn't equal to f1. So, okay, different things sent to different elements. Okay, different inputs sent to different elements. Okay, so that means if you have the same target, you should come from the same thing. Okay, it's a contra positive. Okay, so what's the thing in the group homomorphism that sends to identity? Yeah, kernel. I mean, what's the obvious thing that have to send to identity? If you have a group homomorphism, what's the thing must get sent to identity? Yes, the identity. Okay. So we also know that P of 1G is equal to 1G. Okay. In particular, you already know there's one thing gets sent to the identity, the codomain. Right. So for all the other things get sent to identity, injectivity tells you that all of them must be just the identity. Okay. So your kernel, there's only identity inside. Does it make sense? Okay. We know that this is hence K equals to identity. Okay. So if okay, if you are very stubborn, right? I want to put another one inside here. Okay, which is not the identity. What happened? X is not identity, gets sent to identity, and then identity gets sent to identity. Contradiction to the injectivity. Okay, yeah. Yeah. Is everyone following? Design shooting again. The other side. Not Michelle. 啊，嘉文啊，嘉文，OK 了。嗯，OK 啊。See you a bit confused. Okay, okay. Okay, how about the other direction? Okay, the other direction, suppose K is just the identity. That's the single set. Then we want to show that phi is injective. So to show that phi is injective, what do we have to do? We first suppose px equals to phi y. Okay. Then we want to show x equals to 1. Okay. So how are we going to proceed? Px and phy are the elements in where? Px and phy are elements in the where? G prime. G prime is what kind of set? G group. Okay, so if G prime is a group, how can we play around with this equation? Yes. Okay, so we just put inverse on both sides. Inverse of phi y, for example. Okay. Which is the cancellation law. Okay, which is the cancellation law. So to use cancellation law, right? Make sure you know the inverse axis. Okay, and then you apply on the same side. I'm not sure why some of you apply one on the left, on the right in the assignment. When I give back your assignment, please check. Okay. Okay. So what's the next thing we can do? What's the next thing we can do? Phi inverse. We can combine. Okay, we can combine. Before that, we should move the inverse in first, right? Okay. And then we can combine phi. Okay. Why can we combine phi? Because phi is a group homomorphism. Right? Phi A B equals to phi A times phi. Okay. For all A B. Okay, in particular for X and Y inverse. And then what else can we do? So we know that P sends XY inverse to identity. In particular, what does this mean? So this means that xy inverse is in the kernel of phi. Okay. But what's your kernel of phi? It's just 1. Okay. What's the only thing in there you have to equal to? It's just 1. Okay. Hence, xy inverse equals to 1, which means x equals to 1. Okay. Yeah. Okay. Uh, Typically, algebraic proof is more on structure. Okay, so you need to play around with structure. Okay. Is that everyone okay with the proof? Run okay. How about the back? Okay. Okay. So this proposition is very important. Okay. So if you want to check a group homomorphism is injective, what you need to check, you just need to check that the kernel is only contain identity. That's all. If you know that the kernel contains identity, then your homomorphism is injective. Yeah. This one. Yes, to be precise, you use cancellation. Yeah. Right. So you can use a cancellation of it. Hmm. Okay. Okay. Yeah, what did I say just now? Yeah. So injectivity of group homomorphism is equivalent to kernel containing identity only. Okay. So you just need to check kernel is identity. It's just a singleton set of containing identity. Okay. Okay. So for example, last time we talked about few examples, right? Yeah. So let me pull out my lecture notes. So last time we go through some kernel, right? Okay. So out of these, which one is an injective map? The third one. Only the third one, right? Okay. All the other are not. Uh, the kernel is not the singleton set with identity. Okay. Only the third one is injective. Okay. So in particular, e to the power x, the function, is it injective or not? In the calculus when you learn it, e to the power x is an injective function. It's an increasing and one-to-one function. E to the power x. Yeah. Okay. Increasing and one-to-one. And then the other is not injective. Yeah. Okay. Continue. So next, we introduce another definition. Suppose that x, y is in G. Okay. The element G inverse is called the conjugate of what? What am I doing? So we are I want to choose X, Y, or GA. Okay, maybe just choose GA. So let's take G and A. Okay, and then the element G inverse. Okay, G inverse is called the conjugate of A. B. Of A. Yeah. Okay. So what's the first place you see this kind of object? You conjugate by an element. Can recall G and G inverse. Yes, linear algebra. Where did you see it? Huh? Similarity. Yes. Right. So what's the statement? So A, the matrix A is similar to another matrix B if there exists D such that A equals to D inverse. Or diagonalizable, right? If B is a diagonal matrix, then we say that A is diagonalizable. Okay, soon we will see how important is this. Okay. And then next definition is so so you remember that how useful is this conjugation in linear algebra? How useful is this conjugation? How useful is this? What's the use of conjugation? If you take the product of two conjugates together, it is still a conjugate. So let you see. Huh? Yes, let you see. Okay, so let's say we have a G1A, G. So in a matrix, right? In matrix, so if you can express into this form, okay, dBd inverse. If I want to compute the power of A, how do I compute the power of A? I just multiply dB d inverse n times. Okay, but instead of compute A to the power of n, okay, it's easier to do the computation here. Why? Because the middle term will cancel. Okay? Where you just left with dB to the power n of d inverse. Okay, this is particularly useful when B is diagonal. Right? You take n power of diagonals. You just take power on the diagonals. Okay. Okay. So definition. Definition. So a group, a subgroup, that's denoted as n, is a normal subgroup. Okay. So normal subgroup will play a very important role in group theory. So please take note. Normal subgroup. If for every element in the subgroup, okay, for every element in the subgroup, and for every G in the big G, okay, so how should you think of it? So you have a G, okay, and then you have a N. All the element here, and you take the G outside N, or everything, even inside N, okay. The the condition is the conjugate G and G inverse has to be in N. Okay. So in other words, what does it mean? In other words, G and G inverse is a subset of N. Okay, so this is a definition of normal subgroup. So this is definition. So definition very important is what's the condition here? G and G inverse. There's an equivalent definition actually. Okay, there's an equivalent definition. So and equivalent definition of normal subgroup. Subgroup is the group satisfying G and G inverse equals to N. Okay, actually you can make it equal. They are equivalent. Okay, so obviously the equal sign implies the subset. Okay, but you can go from one subset inclusion to two subset inclusion. Okay, try and think about it. I think my assignment is out already, right? I didn't put this in, so maybe you can try and do this as an exercise. Okay, it's a good exercise to do. Make sure that these two equivalents are this definition are equivalent. Okay. All right. So next, so very important property. So you see, idea is like this. Just now I tell you kernel. Now I tell you normal. Can you guess what I'm trying to do next? Not quite. So normal is an adjective. Kernel is an element. So adjective has to live on the object, right? Okay, you are too advanced already. that one will be done maybe 2 weeks, in 1 week or 2 weeks. I think 2 weeks time. Too advanced. Okay, but what we will show instead is every kernel is a normal subgroup now. Yeah. And then later we will see that actually every normal can be get from some kernel. Yeah, that one is very hard. So we'll do it later. Okay, so the next thing we'll do is the kernel of a homomorphism is a normal subgroup. Okay, so you need to try and guess ahead. Okay, the kernel of a homomorphism is a normal subgroup. Okay. So we want to show that something is a normal subgroup. So we need to go back to definition. Okay, definition of normal subgroup. So definition of normal subgroup says what? For every element in your subgroup, okay, I have to conjugate with any element in G. And then we show that actually this conjugate is in our subgroup. Okay. So our subgroup in this case is what? Is what? Kernel. Okay. So that means I take anything from the kernel, I conjugate with anything with my group. The conjugate must still be in my, what's the subgroup in this case? Our case, kernel. Okay. So to prove something is in the kernel, what does the thing have to satisfy? Under the homomorphism, it will be mapped to identity. Okay, this is what you need to show. Okay, so let's take an element from the kernel. Now phi. Okay, let's call it phi here. And then take phi. And then also take G in our group. Okay. Then have G X G inverse. Okay. Then we conjugate X. And then we conjugate by G. Okay, we conjugate X by G, where we get G X G inverse. So we're going to check that whether this guy is in the kernel or not. Okay, so we need to evaluate under phi. So is phi of g x g inverse equal to identity or not? Okay, this is the question. Okay, is this equal to identity? Okay, so what should we do? Phi of g x g inverse. 雪梅，这是雪梅啊，雪燕，哎，雪燕and 雪梅 right? Okay, 雪梅。What can we do? P of a bunch of elements times together. What can we do? This Chinese phrase. Chinese phrase. There's a Chinese phrase. 则天下大事，合久必分，分久必合。Okay. Right. 合久必分，分久必合。Okay. They are stick together. We want to break it. Okay. Now we want to break it. How to break it? We want to break it. Can we break it? How? Huh? Yes, homomorphism. So phi of g x g inverse equal to what? Phi of g, phi of x, and phi of g inverse. Okay. So what's the next thing we can do? Huh? Can we compute or not? Can I move this inverse across? Huh? Sure. It's not know whether it's abelian or not. We cannot compute. Okay. So one the obvious thing is to send x to identity. Okay. So why? Because x is in the kernel of phi. Right? This is the condition here. Okay, the first thing you do. Okay, first thing you started with. So when you apply with identity, then although they don't commute, but because of this identity, they get together again. The inverse and G and G inverse. Okay. So is it clear how to go from there to the end? What do you do next? There are several ways to go about this. Okay. One way is to just realize that phi g inverse is phi g bracket inverse. Okay. Or what's the other way you can do? Huh? Combine again. 合久必分，分久必合。Okay. Combine again. Phi g inverse. Okay. Phi g inverse is equal to P of 1G. Which have to set to identity. Okay. Okay. So in this case here, what are the example? Have we done? I think we are done, right? Yeah, that's all. We're done. So what kind of example we have seen already? Okay. So for example, right. So I think we need to introduce some notation. If H is a normal subgroup of G, okay, we will write H is less than or equal to G, but we'll put a triangle here. Okay, normal subgroup of G. Okay. I think this is not the first time I do analogy with group with a human relation, right? Last time I also talked about the group definition. What's the group definition? You have inverse your identity, associativity. Okay. Last time I also do some analogy on human, right? Actually, equivalence relation also. So example. Yeah, social sign. And do you know the Israel is having war now? Yes. Yeah. So please pray, otherwise the missile will come here. Someday, maybe. Okay. Yeah, so what are the not missile? What are the normal subgroup? Okay. For example, in GLN, okay. So these things are interested by physicists because when you take experiment, the data live in Rn. Okay. In nature. So GRN. So what's the normal subgroup you have seen already? Special linear group. Okay, SLN. Okay, why? Because this is the kernel of the determinant map. Okay, this is the kernel of the determinant map. Okay, determinant map matrices to real number. Okay, what's the identity for multiplicative real numbers? 1. Okay, so all the determinant 1 matrices, SLN. Okay. How about symmetric group? What's the normal subgroup in symmetric group? Alternating group. Okay, these are all the set of even permutation. Right. So this is the kernel of what map? Kernel of sign map. Okay. So sign map send even permutation to 1. Okay, 1 minus 1. And what else? G. Okay, this one throw away first. Let's do another one. This one. Okay. What's the normal subgroup of multiplicative complex number? Unique circle. Okay. So this is a kernel of what map? Conjugate. Oh, okay. Yeah, it's related to conjugate. But what's the function doing? What's the function doing? Taking the norm or length of the complex number. Okay. How you do it? You have to apply with conjugate. And then what? Then what's the normal subgroup in R? Okay. What we met is Z. Okay. When we consider the ring map. Okay. Yeah. Okay, so these are the examples. By the way, I think I post up Dulik's lecture notes, right? Okay. When you prepare for this course, you read my pre-reads order, and then you go to Dulik's notes, and then if there are similar topics, you can read about it. Because my order and its order is a bit different. Okay, and then Dulip's not there's a good things, which is the reason why I put on, is there's a lot of examples. Okay, so you can dig example from there. Okay, and then I think there's a lot of detail set inside too, if you have problem showing something. Okay, so you follow my order, and then you can read extra example from there. Okay, I think they're doing quite details there. Okay, okay. So don't just follow his note because I'm not following his note. Okay, I'm following textbook, and then okay, the main textbook I use is Artin. Okay, you should based on Artin, and then I will put in more things from the other two, from the Judson and the other guy, Friday. Yeah. Okay, so the main thing is Artin. Okay. Okay. So next proposition. So every subgroup of an abelian group is normal. Okay. Every subgroup of an abelian group is normal. Okay, it's normal. Any idea? Any subgroup of an abelian group is normal. And like first time got one person like very very proactive, 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 very proactive. You know what's proactive? What's proactive? I think don't know. 积极，积极，积极。It's okay. Okay, then yes, answer. Okay. Does everyone know what he's? Does everyone else understand what he's saying? Okay. So to understand what he's saying, you need to have the definition of normal in your mind first. Okay, what's the definition of normal in your mind? So let's prove it. Okay, your answer is correct. Okay, let me say it out loud. Okay, so let K be a subgroup of an abelian group. Okay. What do we want to show? Actually, we want to show G K G inverse. Okay, is in K for all G in G. Okay, which the G here. Okay, you might be wondering where's the G? I didn't write G, so this G here should be the abelian group. Should be in abelian group. Okay, so this is what we want to show. Okay, we want to show that this is true for. Okay, what this means? So this means for all A in K, okay, G and G inverse is in K. Okay. Okay. So what did Jinko say? We know what? We know A is in K. In particular, K is also in G. Okay. And G is already in G. Okay. Of course, if G in G, G inverse is also in G. Okay. So if it's in G, multiplication in G in an abelian group is commutative. Okay. Just now we cannot commute, but now we can commute already. Okay. So G and G inverse is equals to G inverse A. Okay. Which means this is equals to identity times A, which is just A. And A is by definition in A. Assumption. Okay. So every subgroup of an abelian group is normal. Okay. So this means what? This means every subgroup of an abelian group is normal. Subgroup of an abelian group is normal. So last time what we have we found? We found that every subgroup of a cyclic group is cyclic. And then cyclic is a normal subgroup. Every subgroup of a normal subgroup is also normal. So this means cyclic groups are also normal. So you need to try and piece all these words together. So whenever you found a word, there's a relation between abelian and normal. And then last time I told you there's a relation between cyclic and normal. Okay, then try and link them together. Okay, this is what mathematics is doing. Okay. So before you graduate, you need to know how to connect ideas. Okay. Next. So next definition, the center. Okay, after this definition, we will take a break. Okay. A center of a group G. Okay. Often we will denote by that. Okay. Is the set of elements that commute. Okay, that commute with every element of G. Okay. So Z is what? Z is equals to all the elements in G such that Zx equals to Xz for all X. Okay. So like just now we say, a group might not be commutative, but how about we found some elements that can commute with others? Maybe not all of them will commute, but some of them commute. And then we will call these guys center. Okay. Does it make sense? Okay. So if you want to be a center, make sure you can commute with every guy. Okay, why 10 or not? You need to commute with every person to be the center. Okay. Okay. Okay, make sure you can commute with every guy, then you can be the center. Okay. So remark. So this is always a normal subgroup of G. Okay. So this is always a normal subgroup of G. Do you know why? Why? And Seng, you believe me? So say why? I don't know. Anyone know why? Very simple idea here. So why? Huh? You can commute then? Why is it? Of course, how to use the previous theorem.
One subgroup of the abelian group is.
Okay, so how is this a subgroup of an abelian group? So first of all, you said that the center of a group is a subgroup. Well, I haven't proved yet, right? I just said it's a set of elements. I haven't proved. So why is this a subgroup? Now, why is this a subgroup? So to show that this center is a subgroup, what you need to show? Yeah, Q property. What property? Closure. Okay, so if Z can commute Y can commute. ZY can commute with the rest or not? Check. Okay. And then identity. Identity can commute with anyone or not?
Yes.
Inverse. Can inverse commute? Not quite. Inverse. If I have this equation here, can I do cancellation law? If I do cancellation law, what happens? So x equals to z inverse xz, and then xz inverse equals to z inverse x. So z inverse, okay, wait, can you guys see? So z inverse also commute. Okay, so inverse is also in there. So it's a subgroup. Okay, in particular, this is a abelian subgroup. Why is it abelian? I just say can commute with G. Within themselves can commute or not? Huh? Within themselves can commute or not? Can commute? Within themselves can commute or not? Why? Within themselves can commute or not? So let's say Z and Y satisfy ZX equals to SZ. So does ZY equals to YZ or not? Why? Means you, huh? What do you want to say? Because they are element in this group. No. More detail, not detail enough. Means you want to say anything? If Z satisfies this equation, Y satisfies this equation, is ZY equals to YZ. Why? Simple. No. Why? How about have some new friend? I ever heard sound from new friend. Summary. It's a ring. You know why? If Z and Y is in this group, ZY equals to YZ. You know why? You've taken this course before, is it? Okay. Yanke. You know why? No. Okay. How about Tian? Where is Tian? Why is that? Why is that? No. Didn't thought of it. Just stay on that equation. Stay on that equation. Stay there. Stay until you know. Why is that? Why is that? Yes, your Z and Y is G. And then Z and Y have to satisfy the commuting relation for all elements in G, in particular Z and Y. Okay. So this means what? So this group of person is in the center, right? So this center have to be able to commute with every element in the group. And within themselves, they need to commute. Okay. Can get it or not? Okay. So to be inside the center, so if you want to be a center, okay, you need to commute with everyone else. And then within yourself, you also have to commute. Okay. So only this group of person can be in the center. Okay. It's okay. Okay. Sometimes what I say, I have several meanings, depend on how you listen. Okay. Yeah. One person is easy to commute. Right? I only need to commute with myself. Okay? But if this center have more, then they have to commute within themselves. Yeah. No, you mean only singleton, is it? Singleton set, is it? Yeah, singleton set, then 0 plus 0 equals to 0 plus 0. That's the only thing you can take. Yeah. Okay. So if you want to take two things from a singleton set, what's the two things you can take? It's the same thing. Yeah, that's all. Okay. You cannot take two different things. Okay. Because when I say take two things, I didn't say must take two different things. No. Okay. Just take whatever you can take. Okay. How about we take a break and then we will continue with the example. Okay, until 9:08. Hey, Yinke, can you come here for?一个插一件，不要插一件。OK，跟景区慢一点再起，但是每次你一定要插邮件跟新的声音，不然我联络不到你。OK，and then 为什么我还没交这声音？错过了，你就算了，你不想再做了？没有啊？什么？就以为没有错过，你还可以交，但是我每一天就会扣分，所以你还想加，你不想加？要交，因为等我派回去的时候，就不会再做。你能不能这个礼拜有什么发烧啊，什么东西啊，你都可以告诉我啊。因为不然我不知道你发生什么事情啊，我们交代，可以吗？要晚还是可以，没问题。但是你跟我说一声就好啊。还有那个邮件的那个你要，好，这样，好。是深，是但对，所以我应该讲就是你每一次，但你上波幅是一定有发生的。一定有的是什么？比如说，preview 就是一个 sample，比如说就是 identity。了解，我觉得你理解不了，只是好。但是第一个是他应该是改那边然后转。你答案是什么？你答案只是说他是这个 group， 当然是这个 group 啊。我问题就因为我要重点，重点就是就两个在 G， 他要 satisfy 他在 G， 我才可以开始用那个。就是你看那个 screen， 就是我要 satisfy 这个东西，我才可以开始用这 equation。如果我不知道我的 z 和 y 是在 G 的话，我怎么开始用？刚才你说什么？你刚才说 z 跟 y 是在这个 group 里面。对呀、当然是在 group 里面。我已经开始，我都讲这个 z 跟 y 在 group 里面了。所以在这个 group 里面，怎么开始用这个 equation 呢？要开始用这个 equation， 我们一定要符合这个条件。我知道，我就是在问一个很 obvious 的东西，但是问题是，哎，怎样跟你讲呢？就是 OK 啦，撇除这些东西都不要看 ，OK， 不要看这些东西啊。
这句话怎样会问？这个 predicate 怎样问？啊，这样问，还要在 G 里面才可以问。我现在只问你，如果他在 G 里面，然后为什么这个会问？我的问题是这个，然后你又跟我讲他在这个 Z 里面，我都跟你讲他在 Z 里面啊，你又跟我讲在 Z 里面，在 Z 里面做么呢？在 Z 里面，因为我有这个 predicate，我没有讲你是错，我只是说你不是我要的答案，
不够完整。
不是我要的答案，我都已经在这个里面了，所以我为什么还对？就是因为这个里面的这个条件给我。如果这个里面这个条件不是这个，我就没有了。我没有讲你错。
老师，这不是很像他的 inverse element， inverse element， 因为inverse element 要等于 identity， 这个不用，这个只是转移。不用等于 identity，inverse element 要等于 identity。而且inverse element 是 unique 的，这个是它跟所有人commute。每一个人，它要跟每个人 inverse 只是我跟他吧，我跟我的 inverse， 这个是跟所有的，一个东西跟所有的全部都 commute， 全部都 commute。不管是谁来都可以 commute。啊 ，center physical meaning 就是你做这个 process 先，跟做那个 process，和你倒转一下，它给出来的 result 是一样的。这个东西很重要。 你本身有那个
啊，
你本身肯定很多这个。我刚刚有一个 proof identity， 突然两个，一个 G， 然后 A。G inverse 那个不是那个 phi x confidence identity 那个 quantum，
它如果 commute 的话，他们可以 simultaneously diagonalize 那个 matrix。
对，
就是说它 exists 一 set 的 eigenvector such that 全部人都可以 decompose 去 diagonal。这 commute 的commute 就是说，不管我做哪个 process 先都可以。
就你的 lecture 忘了，一种想问一下，哎，我拿我的 ，OK， 你酒啊，糖原之酒，你在吃。这个都不一样的。false true false， 不是在1就是在2应该。这个答案这个答什么？这个对一上就这边嘛。在讲。
OK， 我是这样，你看这边，我要 prove 这个。and then
你这边出什么？这不可以。
对，这个是其实我在讲这个 implies Q，so for every 这个 imply 这个 ，OK， 因为我的条件是这个 proof 是这样子读下来，就是蓝色的字是一起的，这个是 astronomy， 可能比较好把它变颜色，but 就是我有知道 x 不在 A 里面，这样我一定知道 x 在 B 里面。为什么呢？这只普通的 logic 罢了，所以我把这个东西放出来，就是说这句话什么时候对？这句话对的时候是两个都对，或者一个对，一个错，一个对，一个错，整句错。所以我要看的是这句话对，所以有三个情况，这三个情况。如果第一个错的话，
那个 P
是哪一个？这个 P 的话是指这个，
这个
这个是 P， 这个是 Q。
那个老师知道密码？有吗？
没有记起来。
这个是 P， 这是
OK， 然后
那个 bullet expression，
对，
这种。那你 bullet expression 这个 force and true 这个叫 force，我不懂啊，这个如果 bullet expression 的这个
不是啊，这个是 implication 哦。Force 可以 implies everything 啊。Boolean 有几个 operation 嘛 ，and 啊，or 啊，然后 and 和 or 啦，其实，但是这个不是 and 和 or，这个是 imply 可以写成 and 和 or 的 form。But anyway，就是说，就是说什么呢？就是说，
对，这个这个要讲 P 的话，所以你要看 Q 是对还是错的。
对，没有错，
这里有，
对，没有错。
所以如果你这个告诉你这个 true 这个大概在 A 里面，是到 B 的，所以它的 is not an element of A 的话，true 还是它是在 is an element of A，
对，如果 true 的话就在 A 里面，不 true 的话不在 A 里面。
true 是等于
OK，等一下可能要开始先，等下我再跟你讲。
Subgroup of G 还是 normal subgroup of Z？
No, wait, which one?
在
Normal subgroup of G. That is a normal subgroup of G. Right. So Z is the subgroup we are talking about here. Okay, so Z is the normal subgroup of G. Okay. Z is the normal subgroup of G. Let me test this. Okay. Venus is not here. 乐天、韦泽、上娥、严科、德瑞、雷、Raylan、至于金星、顺灵、感人、金波、华英、P 炫、英奇、何怡、雪岩、嘉业、action 李凯。Hey, Li Kai, why are you late today? Oversleep. Play again last night. Huh? 严家。云家 also disappeared today. 啊，家。文硕。一定。玉维。严博。陈烨。林晶。董洁。一周。周和丁呀。丁宇。柳晴。真诚。硕宁啊。硕宁啊。硕宁 not here. 陈烨 where is 硕宁 ？You don't know. He never skipped class 1. 鼓励 ，OK， 子谦、何轩、莹莹、Grace、海燕、嘉文、明秀、Michelle、Ryan、Michelle 还在哪？哦 ，Slade、Ellie、简梅、子源 ，OK。Okay, so can you relate this normal subgroup, this center to normal or not? What's the normal need to satisfy? Normal subgroup. You need to satisfy G and G inverse is a subset of N. So this is N. So center Z G equals to GZ. Okay, stronger a bit. So if I G in, sorry, maybe choose what? Choose a little Z in Z. Then Z to everything is equal to everything to Z. Okay, even stronger actually. So for all G in G, ZG equals to GZ. Okay, but what happened in normal subgroup? Okay. Normal subgroup says for every A in N, GA, G inverse is in N. Okay, so it's in N. We don't know what is in N. Okay, we don't know what does it equal to in N. Okay, it can be equal to A, can be equal to something else in N. Okay, where possibly A not equals to B. Okay, so what can you see here? What can you see here? What can you see here? So to use cancellation law, maybe you can get GA equals to BG. Okay, so what can you see here? What can you see here? Normal subgroup is kind of a weaker version of center. Right. So for normal subgroup, A and B may be different, but center is when A and B is the same. Okay. So normal subgroup is kind of a weaker version of center. So if you cannot find center inside your group, maybe you can try and find whether there's a normal subgroup or not. So this means what? This means what? Weaker. So this means center is always a normal subgroup. A normal subgroup might not be a. Yeah. Okay. So you need to be aware of this element of, okay. Maybe it equal to something else inside the element is enough. Okay, no need to be the same as A. Okay, so example. So I will give you example yet. So SL2 R. Okay, is this a abelian group or not? No. Okay, this is not an abelian group. Okay, this is a matrix subgroup. Okay, this is not abelian. Okay. Not sure. Maybe can you try these two and try and compute whether they commute with each other or not? I believe no. You can try. If AB equals to BN. Okay. So this is not an abelian group. Okay. But okay, we can find the center. So meaning we can find someone that commute with every other element. Okay. So what's your guess inside the center? Who is the one that can commute with everyone else? First, identity must be in there, okay, because identity commutes with everyone else. Okay, who else? Got idea? Inverse of who? Inverse of who? Inverse of who? Huh? Inverse of who? Describe what? I mean, wait. I don't believe you don't know how to describe. I think that thing doesn't exist. It doesn't exist. How to describe? Okay, you must talk about something that exists. Things are. Okay, identity, and then who else? A little bit different for identity. What? Yeah, a little bit different from identity. That has determinant one. Sorry? Inverse of an identity. Inverse of an identity is what? The identity. Identity. Huh? Minus identity. Okay. Minus identity, minus one on the diagonal, you still get determinant one. Okay. So these are the only two actually in this case. Okay. So identity is always in there because just now we already proved it. Center have to be a subgroup. Okay, identity is always in the center. And center of GLN should be all the scalar matrix. Scalar matrices. Okay. I mean diagonal matrix, not scalar. Sorry, diagonal matrix. Okay, so this is the first one. Second one. Okay, how about the center of Sn? Sn is what? Do you remember? No? Set of permutation of n indexes. Sn. Last assignment we did exercise on Sn, right? The cycle 1, 2, 3, 4, Sn. Okay, permuting n elements. So that group is not commutative. Okay, it's not abelian. Okay, so what's the center? When you compute, did you find anything that can commute or not? What is the thing? Disjoint, right? Disjoint set. So, but this only disjoint set that can commute. If you take a random transposition, it doesn't commute with anything. Okay? Because in the center, you need to commute with every guy, not just things that are disjoint from you. Okay? You cannot say I disjoint from you, I can commute with you, but I cannot commute with the other guy. Cannot. Okay? In center, you must be able to commute with every guy, every person. Okay? Every element. Okay. So you need to commute with every person. Okay. You cannot selectively commute. Okay. So Z of Sn is actually just the identity actually. Okay. For n greater or equal to 3. Okay. For n greater or equal to 3. Okay. Why I fix n greater or equal to 3? S2 what happened? In S2. And identity and the transposition 1, 2. So everything commute with each other there. Okay. But when n greater or equal to 3, you start to get a non-abelian group. And then the identity is just the center is just the identity. Okay. So this makes this group a bit hard to study. Okay, because there's no center here. And then a lot of fun things grew out from this SM. Easy things, easy to study. Hard things, very hard to study. And then, because why is it hard? Because there are a lot of structure inside it. So these are the structure that we exploit. Okay, we exploit this structure. Okay, in research, we exploit this structure. So next, okay, I want to describe one morphism to you, and then see how far I can go. So there's an interesting morphism here. I urge you to play around with this morphism. Okay. Back in my time, our lecturer didn't teach us this, but when I read about it in the textbook, I found it very intriguing, very interesting. So let's find a morphism from S4 to S3. Okay.
So how do you send a cycle in S4 to S3? Okay, how do we do this? Okay, how do we describe an X element in S4 in S3? Okay. So there are three ways. So first of all, there are three ways to partition 1, 2, 3, 4, okay, into pairs, okay, into pairs of subset of order 2, okay, order 2. So the three sets we have is, let's call it pi 1, pi 2, and pi 3. Okay, so the first set is containing 1, 2 in a set, okay, and then disjoint union with 3, 4. Okay, and then the second set is, what are the three ways to partition 4 indexes into pair of subset? What's the other two choice we can do? Do you know what's the question is asking about? 1, 3, and 2, 4. Okay, what's the other one? 1, 4, and 2, 3, and that's all. Okay, so we split 4 indexes into 3 partitions, 3 kind of partitions. Okay, so how do we build a map from S4 to S3? Okay, so S4 is the things that commute 4 indexes. Okay, S3 is a thing that permute 3 indexes. Okay, so by commuting 4 indexes here, we can commute these 3 subsets. Okay, so for example, let's do for example 1, 2, 3, 4. Okay, let's try 1, 2, 3, 4. Okay, so what happens if I apply 1, 2, 3, 4 to pi 1? What happens if I apply 1, 2, 3, 4 in pi 1? What happens if I apply 1, 2, 3, 4 on pi 1? How do I commute the indexes inside the set? 1 becomes 2, 2 becomes 3, 3 becomes 4, 4 becomes 1. Okay, so what's this set here? 2, 3, and 1, 4. We are sending pi 1 to pi 3. Okay, so we are sending 1 to 3 now. Okay, and then what happens if I do on pi 2? Okay, what do I get? If I apply 1, 2, 3, 4 to pi 2, sorry, 1, 2, 3, 4 to pi 2, what do I get? I get 2, 4 union with 3, 1. So what's this set? Pi 2? Okay, so we fix pi 2 in this case. Okay, how about pi 3? Pi 3 gets sent to where? 1 sends to 2, 4 sends to 1, 2 sends to 3, 3 sends to 4. What is this? 1, 2, 3, 4. 1, 2, and 3, 4. Which set is this? Pi 1. Okay, so this is pi 1. So altogether, what happens? Pi 1 gets sent to pi 3. Pi 2 got fixed. Pi 3 to pi 1. We will send this 1, 2, 3, 4
to a cycle in to a transposition in S3, which is 1, 3. Okay. Okay or not? Okay. You can play around with this morphism. You can start with any element in S4 and then try and add it on this set and then see what element in S3 you get. Okay, so this is the homomorphism. Okay, so to show that this is homomorphism, you need to check the phi AB equals to phi A times phi B. Okay, but I will tell you this is a homomorphism. So in particular, a homomorphism, we can look at the kernel. Okay, we can look at the kernel. So kernel means what is the things, okay, that gets sent in S4 that gets sent to identity in S3. Okay. Okay. How to get 1, 3? So how to get 1, 3 is to look at how these pi get sent. Okay. So from 1, 2, 3, 4, we can see that pi 1 gets sent to pi 3, pi 2 got fixed, and then pi 3 gets sent to pi 1. Okay. So what's the permutation related to this map? 1 to 3, 2 fixed, 3 to 1. What's the permutation that do this? 1, 3. Okay, so we will send 1, 2, 3, 4 to 1, 3 in S3. Is it okay? Yeah, you can try with other elements in S4. Okay, and let's see how it add on this pi 1, pi 2, and pi 3. Okay, and then they will get an element. You will always get an element in S3. Okay. So the identity element in S3 means what? It fixes pi 1, fixes pi 2, fixes pi 3. Okay. So what are the elements in X4? When you permute 1, 2, 3, 4, you fixes every one of them. Okay. What are them? So let me tell you the answer and then you think about it. So the kernel of phi is exactly, first of all, identity must be in there. And disjoint cycle of 1, 2, 3, 4, disjoint cycle of 1, 3, 2, 4, and disjoint cycle of 1, 4, 2, 3. Okay. So meaning they just commute among themselves within the set. Okay. So that you can fix every one of them. Okay. And then this is the very famous group. So this is the group of order 4, right? So last time I mentioned a fact to you when I introduced the multiplicative table. How many groups of order 4? You remember? There are only 2 groups of order 4 elements. Okay. So one of them is Z4, the other one is Z2 cross Z2. Okay. These are the only 2 groups of order 4. Okay. So out of these 2, which one do you think this kernel of phi looks closer or looks similar? Okay. So you can see that these items here, right? Order 2. Order of elements means what? How many times you compose with yourself, go back to identity. Okay. So these are products of transposition. Okay, correct? So for example, if you do 1, 2, 3, 4, and then square it, what do you get? You get identity, right? Because disjoint cycle, they commute. Okay, and then they cancel out. Right? They commute. And then you commute to identity. Okay. So in particular, this is actually Z4 cross Z2 cross Z2. Okay. And soon I will tell you now what is isomorphism. How we show these guys are isomorphic. How can we show they are isomorphic? Okay. And then in the assignment, I asked you to show that Z4 is not isomorphic to Z2 cross Z2. Okay.
So this phi is a way to build the Z2 cross Z2. And then this group is what? Okay, so Z4 is the cyclic group. And Z2 is what we call the Klein 4 group. Okay, so Z2 cross Z2 is what we call the Klein 4 groups. And then maybe you heard about Klein water before, right? There's relation between this Klein 4 groups and the Klein water. Okay. So if you go to algebraic topology, you'll come across a group called fundamental group. Okay, this is a group built up by loops on the manifold. Okay, loops on manifold. So loops composed with loops is still a loops. Okay, so it forms a group. Okay, and then the fundamental group of Klein water is Z2 cross Z2. Yeah, we attach a group to a manifold. Okay, this is what an algebraic topology do. Yeah. No, it's a set of loops on the manifold. What do you mean by generator for manifold? How do you generate a manifold? What's fundamental solution? Different. It's a bit different. Yeah, it's not the same fundamental, I think. Yeah. Yeah, fundamental group just means set of loops on the manifold. Okay. Yeah. Yeah, okay. So next, so how we deal with these how to say two groups are the same. Okay, how we consider whether two groups are the same or different. Okay. So there comes this definition here. So this definition will help you do the assignment question. So an isomorphism, okay, from G to G prime, okay, is a bijective group homomorphism. Okay, so that's all. How to be isomorphic? They need to have a bijective map, which is also a group homomorphism. Okay. Bijective plus group homomorphism is isomorphism. Okay. So in this case, okay, so if there exists an isomorphism, okay, we will write G is isomorphic to G prime. So there's a 3-line equalities here. Okay. In latex, this thing is called /con. If G is con G prime. Yeah. In latex, you will type this. I don't want to continue that song. Yeah. Okay. G is con G prime. G con G prime.
So no clear.
Huh? No K. Okay, no K. Okay. Okay, so it's a bijective. Okay, bijective group homomorphism. And then let's see what kind of isomorphism you have seen before. Okay, what kind of example you actually seen before, but we might not realize. Okay, so for example, the EX from R plus to R cross. Okay, so just now we see that the kernel is 0, right? In particular, this map is already injective. But why is it surjective? Yeah. Because the inverse exists. Inverse of E exists. Inverse of exponential map is what? Calculus.
inverse of E1 is log. Yeah, okay. Logarithm. Okay, logarithm to natural base E is inverse of E. Okay. And then what kind of map? Okay, and then last time I talked about this equivalent way of stating Sn in terms of Pn, right? The permutation matrix. Okay. So there's an isomorphism between these two. The way I constructed permutation matrix from Sn is the isomorphism. Okay. This means what? I can send a permutation to a permutation matrix, and then from the permutation matrix, recover the permutation. Okay, so my process is reversible, and then it is unique and not unique. So let me try and write down what I'm trying to say. Okay, so I give you a way. Okay, so I give you a way going from Sn Pn. Still remember the way or not? You remember the way? I need to describe again, is it? Okay, so I have a permutation in Sn. Okay, so I have a permutation in Sn. Okay. And then in particular, this guy permutes the indexes 1 to n. Okay, so the permute indexes is 1 to n. Okay, so how do I send to a permutation matrix here? Okay, I send to the permutation matrix that does the same permutation on E1, E2 up to En. Okay, so we map 1 to E1, 2 to E2, and then so on, n to En. Okay, and then we see how the permutation permutes 1 to n, and then we will take the permutation matrix that permute the same way for E1 up to En. Okay, can remember now? And then a lot of you do so there are two conventions in a matrix. Either row vectors times a matrix or a matrix times a column vector. Okay, so how does my matrix add on E1, E2, E3 up to En? We use matrix and column vector convention. Okay. So this process here, let's say we call it phi. Okay, we can go backward. We can produce the phi inverse. How do we go backward? Exactly the same. We start with a permutation matrix. Okay, and then we see how it permutes E1 up to En. And then we map it to a permutation in Sn that commute the same way it commutes 1 to n. And then show that phi inverse is equal to identity and phi inverse phi is equal to identity. Okay, so meaning what? Okay, I'm going to tell you what this means. Okay, so meaning, for example, if I do the first one, what do I do? So I start with a permutation. Okay, I start with a permutation, and then I send it across by phi. Okay, and then I send it back phi inverse. I should get the same permutation in Sn. Okay, and then for the next one means if I start with the codomain, I go to inverse. Okay, and then I send it across phi. I should get back the same permutation matrix. Okay, this is what phi inverse phi identity and phi inverse identity means. Okay, I will show you future how to use this to prove stuff. Okay, I mean how to prove this kind of statement. Okay. Okay, so let's continue first. So So there's a lemma. So if P G to G prime is an isomorphism, then the inverse P inverse from G prime to G is also an isomorphism. Is it clear why this is true? If P is an isomorphism, what does it mean? Definition. Yeah, so phi, first of all, is a group homomorphism. And what? And it is bijective. Okay. So since it is bijective, right? What does it mean? Yes. Okay. Since it is bijective, the inverse exists. Okay. Since phi is bijective, phi inverse exists. Okay. Phi inverse exists. But is phi a group homomorphism or not? So phi inverse exists, right? Okay. To show that phi inverse is an isomorphism, what do you need to show? You need to show two things. Phi inverse is a group homomorphism, and then phi is bijective. So is phi inverse bijective or not? Why? Who is the inverse? Phi is the inverse. Phi is the inverse of phi inverse. Okay, so it's bijective. Is it a group homomorphism? You need to check. Okay, you need to check. Okay, so try and check that phi inverse is a group homomorphism. Okay, I'll post solution. Try show that phi inverse is a group homomorphism. In particular, you need to show that phi inverse of AB equals to phi inverse of A times phi inverse of B. Okay. Okay, we still have time. Let's continue. So if G is isomorphic, or this one I wrote already. So two groups. I will introduce another word. So two groups, G and G prime, are said to be isomorphic. Okay. If there is a isomorphism, okay, between them. There's an isomorphism between them. Okay. And similarly, so you see, mathematics is like this. So we have different things. Okay, we have different things. And then maybe they satisfy some property. Then we group them together. And then within this group, right? Yeah, some of them are equivalent under another condition. We group them again. Okay. So you see, we have groups. These are all groups. These elements are all groups. And then within the group, we put on this isomorphism. If there's an isomorphism, we'll say this group is the same, equivalent up to isomorphism. Okay. And then this group, this element from another set, which we call an isomorphism classes. Isomorphism class. So an isomorphism class of G is a set of groups isomorphic to the given group G. Okay. To the given group G. So you should think of it as a equivalence relation. Okay, equivalence relation. So this is an equivalence relation. Equivalence relation says what? 3 properties you need to satisfy. You are equal to yourself. Okay, reflexivity. You are equal to yourself. In particular, G is isomorphic to itself. What's the isomorphism you can take? G is isomorphic to G itself. What's the isomorphism you can take? What's the map from G to G that is isomorphic? That's the isomorphism. What's the obvious map from G to G? Small g to small g. So what's that map? Identity map. Okay, identity map is an obvious group homomorphism. Okay, so you are equal to yourself. Next, what's the next? Reflexivity and then symmetric. Symmetric. So if G is isomorphic to G prime, is G prime isomorphic to G? Is it symmetric? Symmetric? Is it symmetric? Well, let me check first before. But for isomorphism, is it symmetric? Is this relation symmetric or not? If I'm the same with you, are you the same with me? Okay, if I can find an isomorphism to you, can I find an isomorphism back? Yes, right. This is what we have proved just now. Okay, we've proven just now. This one. Okay, phi inverse is the isomorphism. And then transitivity. If G is isomorphic to G prime, and then G prime is isomorphic to G prime prime, is G isomorphic to G prime prime? Okay. If I'm the same with Wensuo, Wensuo is the same as Y. Am I the same as Y? 近朱者赤，近墨者黑。Okay. Right. So how to produce the isomorphism? How to produce the isomorphism? Huh? If I have 2 isomorphisms, how to produce the third isomorphism? How to produce a third isomorphism all the way from E to Y? Huh? How? Say don't do action. Just compose them, right? I compose the isomorphism from me to Wensuo and then Wensuo to Y. Okay. Why is this still an isomorphism? Why the composition of isomorphism is an isomorphism? Huh? Yes, also has the inverse. What's the inverse? What's the inverse? Huh? Okay, very good. Huh? So G and F are isomorphism. Okay. So what's the inverse of GF? What's the inverse? Find me the inverse. F inverse composed with G inverse. Okay, but F inverse, G inverse exists because they are isomorphism. Okay. Then you need to see that why GF is a group homomorphism. Okay. Why the product of a group homomorphism is still, the composition of group homomorphism is still a group homomorphism. But I think it should be easy to see. Okay, should be easy to see. Okay, let me see. Any question before I think we take a break, before we break? Call for the day. Oh, how about give example first and then we will finish. Example finish. Okay, example and then we finish. Okay. I scared later next week you forgot what I said already. Then I have to repeat again. Okay, so okay, last. Okay, so every group of prime order T is cyclic. Okay, So every prime order group is cyclic, and then all groups of order P is isomorphic. Okay, you don't know this, maybe we will prove it later. Okay, but I want to let you see the statement first. And then there are two isomorphism classes of groups of order 4. Okay, so in your assignment, what you have shown is there are two of them. They are not isomorphic, but the question is, why are only these two exist? Okay, so what you shown in the assignment is there are two of them, and then they are not the same. Okay, but this statement is why those are the only two. Okay, why those are the only two? Okay, so in this world, there's only two isomorphism classes of group of order 4. Okay, and then this one I think maybe we won't cover. This is in I think 7.8.1. There are 5 isomorphism classes of order 12. Okay, and then I want to stop with one theorem and then we can leave. So this is a very important theorem in finite group theory. So this is called the Cayley theorem. So Cayley theorem says that every finite group is isomorphic. Okay, every finite group is actually the same as a group of permutation. So it's a subgroup inside Sn. Okay, so that's why it makes Xn so intriguing, so interesting, because you can find all the finite group in this world Sn. Okay, and then we will prove this in next lecture. Prove the Cayley's theorem. Every finite group is just some subgroup of Sn. So we just study Sn is enough. So we'll see you next week.